It's great to be here, and as the man says, my name's Russ Olsen. I also have the Twitter handle, remarkably enough. It turns out it's a fairly unusual name, so I can get all of the stuff. And I work for a company called Cognitech, as was mentioned. We're the people behind Clojure. So if you're interested in functional programming or Clojure or Lisp programming languages, do come hunt me down during the conference sometime. But I want to start with a question. And the question is, what's holding us back? Why aren't we better at this, right? We build these systems, and I have had this feeling for a really long time that we should be better at this. And in fact, it goes all the way back to the beginnings of my career, because I didn't start out as a software developer or a programmer. I started out as a mechanical engineer, which is why I knew something about pneumatic controls. And I found mechanical engineering endlessly frustrating because mechanical engineering is all about limitations, right? If you make a gear, it starts wearing out the day you put it in, right? And there's always friction. You know, we build bearings and there's these high precision things, and the idea is to reduce the friction, but there's always some friction. If you have a beam and you put some force on it, it's going to bend because there's stress. And so mechanical engineers, they have all these equations. This is the equation for friction. This is the equation for stress. If you put some stress on a beam, this is probably the worst one of all. This one is essentially the efficiency of a heat engine. In other words, if I put fuel into a motor or an engine, how much work can I get out of it? And let me tell you, that's always less than 100%. And this sucker is the second law of thermodynamics. It's built into the fabric of the universe. There is no getting around that. And so mechanical engineering, it just kind of drove me crazy. And eventually I got out of mechanical engineering and got into programming, because programming, there aren't those physical limitations, right? When you're, you know, our raw materials, our data, our machines are algorithms and programs, and our output is information, or maybe even wisdom, God help us. And you know, in the time that I've been a programmer, the machines have gotten hundreds of thousands of times faster, right? So the physical limitations are just going through the roof. The disks have gotten millions of times bigger. But the thing is, we haven't gotten a million times better at this. We've gotten some better. We're doing all right. But we are not 100,000 times better than we were 30 years ago or something. We're a bit better. So my question is, what's holding us back? And my answer, well, I have an admission to make. My answer is, it's my fault. It's me. It's my fault. Yep, there you go. But it's not just me. Fortunately, I get to share the blame. These are my colleagues at Cognitech. It's all of our faults, right? There's the people you can point the finger at. But there are some other people who we can blame. It's all of us, right? What's holding us back is us. When your raw materials are data, when your machines are algorithms and programs, and when you're trying to produce wisdom, the thing that holds you back is what's up here. How smart are you? That is the fundamental thing that's holding us back. That's the bad news. The good news is that if you look at everyone in this room, collectively, we are all smarter than we are individually. Every single one of you knows something that all the rest of us would benefit from knowing. You might know something that you might want to know. You know, I might know something, well, I hope so, that you guys might want to know. And the only way we're going to get better at this thing that we are doing is to start explaining it to each other. And so I think that explaining is basically like if making programs or information systems or beautiful designs is what you do for your first job, I think explaining what you do is the second most important thing you do. Because if you can't explain it, eventually somebody's going to say, I don't understand this, and toss it, right? Explaining is an incredibly important part of your job. So what I'm going to talk about this afternoon is 6 ways that you can make your explanations stick better, that you can be better at this thing that is a really important part of your job. So I got 6 pretty basic things that you can think about the next time you're walking down the hallway, right? We think of explaining, right? Maybe I'm sort of a professional explainer, but what I'm doing up here is kind of the least important kind of explaining that goes on. The more important kind of explaining is you're walking down the hall and somebody says, how does that work? And you tell them. That's the key kind of explaining, because that happens a million times more often than what I'm doing up here or someone writing a book. You guys are the key explainers in the world of technology, and it would be helpful, I think, for all of us. You could make your company better, you could make your colleagues more efficient if we were all a little bit smarter. So here's 6 things you can do to make your explanations stick. And number 1 is you need to take explaining seriously, right? It's a key part of your job. And you know, we're programmers or technical people of some sort or other, so there's only one thing we do when we take something seriously. We have a plan, right? We are like planning people, right? Think about the difference between waterfall and Agile, right? Agile, and I'm not talking about like the kind of thing you get certified with. I mean, just the basic idea of Agile, as opposed to, say, the basic idea of waterfall. Agile is this idea, you know, this huge step forward in how we do what we do, and it is, you can sum it up simply by saying, don't overplan everything. Like, plans are really important to us. So I would say that when you go to explain something, have a plan. Just think for a second, how am I going to explain this? And it turns out that if you don't have a plan, well, you have what I think of as the default plan, right? An explanation is kind of, you know, painting a picture. And if you don't have a plan, you kind of have a Picasso, right? There's an ear somewhere, there's an eye somewhere, but it just kind of doesn't fit together, right? So somebody says, how does the system work? And you don't have a plan, you don't think about a plan. So what do? You start telling them about the last thing you worked on, or the first thing you worked on. You talk about the last bug you fixed or the first bug you fixed. You talk about your favorite part of the system, or that bit with the offensive comment or the funny variable name, right? Anything but sort of a reasonable, thought out way. And what you really want your explanations to be more like is a simple Leonardo drawing, right? There's not a lot to it, but it gets the message across and it's organized. All right, so what does a plan for an explanation look like? Well, it turns out there's a few standard ones. There's like patterns for explanations. So, and the most basic one is zoom in. You start with the big picture and you work your way down to the details, right? So, hey, you're going to pair with a new person and you're going to do some work and they're brand new, they were just hired. Well, how do you start? Well, you say, hey, well, we're in the startup and we're trying to get rich selling pet food on the internet. I don't know, right? And that's the big picture. And we're building this e-commerce application and we need a login screen. And you and I are working on the login screen, right? That is a top-down explanation, right? None of this is rocket science. The most perfect example of a top-down explanation that I can think of comes from this guy. This is Abraham Lincoln. And in the most famous speech in US political history, I think, the Gettysburg Address, he starts it by saying, 87 years ago. 87 years ago, the country was founded. That's the big picture. In the last few years, we've been going through this horrific civil war, right? So that's the medium-sized picture. And here we are today, right now, here we are dedicating a cemetery, right? He goes in 3 sentences from the founding of the country to what we are doing today, right? That is a brilliant top-down explanation, or a zoom-in explanation. You can take it the other way. You can start with the small picture and work your way out. Hey, we're working on this login screen because we're building an e-commerce site because we want to get rich selling pet food on the internet. So just work it the other way. So those are 2 patterns for explanations. The third one is a process explanation. Follow something through time, right? Like a car being manufactured. So How does your web application work? Well, the request comes in, it gets authenticated and authorized, it goes off to the controller consults the model, sends it to a view, the view sends the result back out, right? It's following a thing through time. These kind of explanations are so useful and popular, they have their own UML diagram, sequence diagram, I think. And trying to come up with like a popular version of a process explanation. Does anybody still know about Schoolhouse Rock? Yeah, you do, right? So this is a shot from Schoolhouse Rock, little children's thing about how does a bill become a law in the, in the US federal government, right? Congressman proposes it, it gets passed by the House, it gets filibustered in the Senate, that kind of thing, right? So that's a process explanation. But absolutely the most useful pattern for explanations is simple to complex. If you have some complicated thing you need to explain, you start with a cartoon version of it. You blur out all the details and you just give them the very basic kind of blurry, not even real version of it, okay? Because explanations are really not about getting the facts correct. It's about giving the person who's listening the context for fitting the facts together, right? So it's simple. I was trying to think of an example of this. And I'm a Clojure person, and I spend a fair bit of my time explaining Clojure to people who've never seen this programming language before. And so if you're new to Clojure, eventually you're going to come across an expression that looks like that. And what is that, right? So I'm trying to explain, this is day one of Intro to Clojure. Well, I think you're mostly all programmers. Put in some commas. What does that look like? It looks like an array, right? So what do you say? I say, yeah, that's more or less an array, right? It's pretty close to an array. Don't worry about it. We'll talk about why it's not an array later. In fact, that thing in Clojure is a persistent, immutable data structure that's really got a tree kind of structure behind it. But that's not really what you say to a beginner, right? That's too much. You just say, it's an array, right? It's an array. Well, we'll come back to it, right? And the idea is you get them, oh, that's an array, and they put that in context. And then later on, when they're a little stronger, a little more oriented, you come back and you say, hey, that's not really an array. So what am I saying? I'm saying you lie. You just lie, right? You just, not exactly make something up, but make something up, right? Now, this is an incredibly, incredibly effective technique for explaining things, but it has one problem. And the one problem is that sometimes you'll be doing this, and an expert will come by, a Clojure expert, and they will say, stop! Stop, you're lying! No, that's not an array, that's actually a persistent data structure, blah, blah, blah. And the thing to do is to smile and nod and scoop them out of the room and go on lying. Because the world is full of people who know the thing and don't know how to explain the thing. And in particular, the mistake we tend to make is that we tend to forget that if you try and explain everything right now, you will end up explaining nothing forever, right? You can't explain it all right now. So you start with the cartoon version. So in summary, here's what I'm saying. Just ignore the experts, right? The stars stand for a 4-letter word that means ignore. So that's number 2, right? So we have a plan, right? And, well, actually, it's number 1. So have a plan is number 1. So number 2 is be an Agile explainer. And what does it mean to be an Agile explainer? Well, again, I'm not really talking about certified Scrum explaining or anything like that. I think of kind of the gist of Agile is you do the thing, you measure the output, the result, you fix any problems, and then you do it again, right? And you just keep running this loop, okay? So if you think about this in terms of explaining, well, clearly, if you have to explain something, you can come up with some explanation for it. And if you knew what was wrong with your explanation, you could fix it. And obviously, you could go back and do it again. It's the measuring part that is hard with explaining, right? How do you measure the success of your explanations? Well, it pains me to say this. It really does, because I've seen a lot of like obviously failing explanations where the person who's doing the explaining doesn't realize their explanation is failing. So I'm sorry, I'm going to say some things that are pretty obvious right now, but I feel like I have to. How do you determine if your explanation is failing? Well, you look for silence. The person gets real quiet, right? And there's this sort of blank look, like, I have no idea what's going on. But most of all, you start getting the same questions over and over. I don't get this. Could we go back to this? Could you tell me about this again? That means that your explanation is not working and you need to fix your explanation. And let me tell you, if you like take on the mantle of a person who explains things, then you need to have it firmly fixed in your head. It's you, it's not them, okay? Let me tell you what I think excellence in explaining is. Excellence in explaining is not, hey, I've got this person and they're pretty familiar with whatever it is and I'm going to get them up to the next level. There's nothing wrong with that. That's great. It's just not excellence. It's not the high point. The high point of explaining is also not, I've got this expert and I've managed to tell them something they didn't know. That's cool too, but that's not greatness in explaining. Greatness in explaining is when you take a person without a clue and you get them to the point where they can start learning on their own. That is the true goal of explaining. And in order to realize that goal, you have to take the responsibility on yourself. It's always you, it's not them. Fortunately, about half, and I just made that statistic up, about half of all the failures and explanations, explanations have a single very common failure mode, and I think of it as the gap. Okay, and the gap has to do with the way we learn. And it goes like this. If you're learning a foreign language like Spanish, right, and you need the word for red in Spanish, well, if you're a beginner, you just you go through this painful lookup process. What's the word for red in Spanish? And you come up with that word, which all my Spanish-speaking friends tell me for sure I cannot pronounce, so I'll leave it alone, but there's the word, right? But later, as you're getting better at it, if you keep working at Spanish, after a while, you'll just come up with the word without even thinking about it, right? That's kind of the definition of learning, okay? Well, that's great for learning. It's horrible for explaining. The problem is that experts, if you're expert in some field, you know it so well, you forget there is anything to know. And so when you try to explain the thing, you leave these great gaps in the explanation because everybody knows that. Clearly, everybody knows that. And I've now told this story on Dave Bach like 20 times, but I'm going to tell it again. Dave and I, many years ago, had this class in Ruby on Rails. If you have some ambition to build a web application, maybe you have some business idea, you can get together with Dave and I, and we will teach you Ruby on Rails. So we had this room full of people who had more or less, mostly less programming experience, and it's the first day, and we're going to teach them Ruby on Rails, God help us. And so how do you even start? You start with OO programming, model view controller, how to get things installed, a million different things you could start with. I can't remember what we started with. But what I do remember was there was a woman in the back of the room who ended up being one of the better students in that whole exercise. But that first day, she was struggling. And it was clear that we had left a gap a mile wide in our explanation. And I can remember trying to figure out what was it that we didn't explain to her. And she was doing all the things. She was asking the same questions over and over. She was the blank stares and can you go back to this? And finally, it was like I saw the light bulb go on over her head and she figured it out. It was her, it wasn't us. She figured it out on her own and she said, oh, Ruby is the language. Rails is the framework. And I remember standing there thinking, what kind of person would not know that? Everybody knows that except people who might come without a lot of programming experience too. Right? It's you, it's not them. So that's number 2 is watch for the failure modes in your explanations, and in particular, look for the gaps. Next one, number 3. I've got kind of a question for you guys. And my question is, what do files and objects, so think of the things on your disk drive and objects in terms of object-oriented programming, what do they have in common? Now here comes the twist. What do those 3 things have in common? What do hit songs, objects, and files have in common? And what do they have in common with transactions? And what do they have in common with temperature? Right? The answer is, or at least my answer, is that they're all abstractions. None of those things actually exist. You can't actually point at something physical that will fall on your foot and say that's a transaction or a hit song. They're all abstractions. They're higher level ideas. And in a very real sense, we are in the abstraction business, right? You go on some customer site and they say, oh, I'm going to move this money over here to here. And you say, oh, that's a transaction. I have this thing and it does this, that, and the other thing. And you say, oh, that's an object, right? We are in the abstraction business. The problem is that since abstractions, well, it's not really a problem. Abstractions are power, right? The reason we have files is that nobody wants to deal with 10 billion bytes on a disk drive just as 10 billion bytes. So we come up with this file abstraction, and abstractions are these things that let us rise up out of the dirt, right? Like get us up out of the muck so that we can sort of see what's going on. And in particular, every abstraction is there to fix some pain. It's like a painkiller, right? I don't want to deal with the bytes on the disk drive, so I invent files. I don't want to deal with the chaos that is trying to build a complex information system with procedural programming, so I have object-oriented programming. I don't want to deal with the chaos that is trying to build a complex information system with object-oriented programming, so I have functional programming, right? All of those abstractions kill the pain of something, and one of the massive gaps that we tend to leave in our explanations is we explain the abstraction and we forget to explain the pain that is curing, right? So I remember when I was kind of a young student learning about stacks, I had the textbook open and it said, oh, a stack is a bounded, ordered data structure with, what is it, first in, last out, or whatever it is, semantics, and that meant nothing to me. And then I went to class the next day, and the professor got some books out, and he said, think of a stack of books, and you put a red book on top, and then you put a white book on top of that, and you pull the white one off, and you pull the red one off, and I'm like, okay, I got stacks now, right? It pulled, that example pulled it down into the real world, okay? And that's what you need to do when you're trying to explain abstractions, is pull them down into the real world. And the way you do that is with examples. And the absolute most successful example, at least in programming, of all time has got to be our old friend Hello World, right? There's a Hello World for every programming language. This is, I think, the original one in C. And I put it up there in that horrible green because that's how I experienced it the first time, on a green phosphor terminal. And I could still see. And the reason that Hello World is so successful is that it pulls down, a programming language is a bundle of abstractions. And it pulls each programming language down into the real world, something I'm familiar with. I need to compile the program and run it as a command. And so it pulls it from all these abstractions down into something I understand. And that is the key to explaining abstractions with examples, is you need to hook in to what people already know. And I'm kind of practicing when I preach, because if you think of all my examples, I'm at least trying to hook in the things that you already know. So the takeaway here is that when you're building something, abstractions are power, right? Abstractions let you build things easily, but when you're explaining it, it's the specifics that give you clarity. All right, so that's number 3. Number 4 takes me into a place I do not want to go. I am not a sports-oriented person. I don't really like sports. I don't watch them on TV, but I have made an academic study of sports. And I have discovered that the games that people watch on TV, they fall into 2 different categories. In one category, there's baseball, there's golf, and there's tennis, probably a few others. That's one category. In a different category, there's football and hockey and basketball and soccer. So we got and some others. We've got these 2 general categories of sports. What's the difference? Some of them have a clock, and some of them don't. You play baseball until you're done. It could take 9 hours, right? You play football for exactly an hour, or it seems like 9 hours. And the question is, what kind of sport is explaining? We tend to treat it like it's golf or baseball. You need to explain a web application. Well, in inning 1, I'm going to explain the stateless nature of the HTTP protocol, and in inning 2, I'm going to explain the whole history of the internet. In inning 3, it doesn't matter because nobody's listening anymore, right? Explaining is a timed event. There is a clock. When the clock gets to 0, you are done explaining. Oh, your mouth might still be moving, the words might still be coming out, but you are done. Where is the clock? It's in the person you're explaining it to's head, right? We all have a capacity for absorbing information. For some people it's bigger, some people it's smaller. I bet yours was bigger at the beginning of this conference than it is right now after lunch. Thanks. But everybody has a capacity, and every explainer has to be aware of the capacity of the person they're trying to explain things to. And that has an important implication for how you structure your explanation, and that is put the important stuff first, right? So that they will be awake. You know that thing about having a plan for your explanation? That is the most important thing I'm going to tell you today, and that's why it's first. All right. The other thing that you need to keep in mind is that terminology, at least in an initial explanation, is not the important stuff. Ever walk into a math class? This seemed to happen to me like 3 times a semester going through school. Walk into a math class and the professor says, let's start by defining some terms. Oh God, no, let's not. Let's do anything else, right? Terminology is really important. It's important to get the terminology right in the long term, but in the beginning, it's just kind of an impediment. And I'll give you an example. In computer security, there's these 2 important terms, authentication and authorization. They sound alike, and they're kind of long words, right? If you only have a short time to explain something about computer security, take your pick. Which explanation do you think works better? Hey, in computer security, there's these 2 important ideas called authentication and authorization, and the person isn't paying attention anymore, okay? Let's try a different approach. In computer security, there's 2 important ideas. Who are you and what are you allowed to do? And, okay, which of those explanations was actually an explanation, right? You can hang the terms on it later. Get the concepts over first. The other thing to keep in mind about the clock is that it's variable. If you play your cards right, you can make the clock run slower, or you can actually get more time on the clock. On the other hand, you can run that sucker right down to 0 right now. All right? How do you run that sucker right down to 0 right now? Stand in front of a group of people and say, this is really hard. Oh, thanks a lot, right? The reason I think of computer security in this context is I went to a 9-hour seminar once on computer security, sat down, they're going to bring in lunch, we're going to be there the entire day, and the instructor gets up in front of the room and says, most people never get this. Hi, I'm Russ Olsen, and you are all screwed. You know, don't do that, right? Supply people with small victories. Tell them it's hard after they've gotten it. You know the bit about the gap? That is the hardest thing I'm going to tell you today, and we're done. You got it, right? Yay, right? The other thing you can do is you can provide them with a roadmap for where you are in your explanation. That's why I like the 6 things, the 4 things kind of thing. You know where you are. And the good news is we're on thing 5. You're almost done, right? So thing 5 has to do with this. You're a bunch of programmers. What's that acronym mean? Don't repeat yourself. As programmers, we don't like repetition. Nope, we don't. For very good reasons, right? You're building software. You don't want to fix the bug over here and discover it's over here and then over here and over here and there's a variant of over here and it didn't get fixed over there. We don't like repeating ourselves, so we try and dry out our code. But you know, the English word dry has some other meanings, right? Let's explore those other meanings. It means having no adornment, right? He just gave us the dry facts, okay? Or it means impersonal. Oh, that Russ Olsen, he's like the driest person, right? There's nobody there. But probably the most damning one of all, the worst one of all, is without butter. I'll have that toast dry. Yuck. All right, here's the thing. Dry, don't repeat yourself, is for mechanisms. It's for machines. It's for the things we build. It's not for people. You are not a machine, okay? People like repetition, but we are trained so hard to get rid of the repetition in our code that it tends to spill over into when we're explaining things. So I'd like to propose an alternative, which is repeat yourself enough when you're doing explanations. And it turned out I found a bottle of, it's Russell's Reserve Rye. You can find a picture of anything on the internet. So repeat yourself enough. Well, why would you repeat yourself? You repeat yourself for emphasis. Let me say that again. You repeat yourself for emphasis, right? But most of all, you repeat yourself for context, right? Explanations are not just a series of boring facts. They are context. How does this all fit together? And so one of the reasons you repeat yourself is to remind the person this new thing fits in here. And in particular, what you don't want to do is you don't want to sound like a government form, right? You know that thing you're filling out your taxes or some your driver's license thing, and it'll say something like refer back to section 9.7 before proceeding. Can you please give me a hint as to what is in section 9.7? It might be really, really important. Just a little hint. All right, so there it is. That's number 5, which is repeat yourself enough. And now we are on the last one. This is the one you've been waiting for, right? And the last one actually has to do with this book. And I have a copy of it here somewhere. So tip in your explanations is have a physical prop, and the pro tip is to forget that you that you had it in your backpack. So this book, there's a story behind this book, and it is that when I was an undergraduate, I fell in love with this mathematical technique called numerical analysis. And so I spent an entire semester, instead of doing what I was supposed to be doing numerical analysis and learning all about numerical analysis. Now, numerical analysis is this way for solving equations. It's a technique for solving equations if you have a computer and you aren't that smart, okay? And I qualified on both grounds. And the thing with numerical analysis, the details aren't important, but the key thing to know about numerical analysis is usually it gives you a good answer. But very occasionally, it will give you this incredibly awful, not even anywhere close, crazy answer. So that semester, I remember I was working in the library, and I had basically every book that library had about numerical analysis spread out on the table, including this one. Well, bought this one on eBay. I didn't steal it from the library, but a copy of this book. And I was sitting there on this beautiful spring day, and that's what I did in beautiful spring days, is I sat in the library doing numerical analysis. And I looked at this book, and the light was shining on it, and it seemed like there was like something embossed on the cover of this book. And I'm like it looks like words or something, and it's right there. And after a while, I started going a little crazy, right? And after a while, I put a piece of paper down and did that thing that people do on monuments where you kind of scribble on it, and I did that with this one. And there's the word. And God bless you, Ford and S. Acton, right? Whoever you were. That is one small joke. And that was, I hate to admit it, that was like 40 years ago. And I can't remember a single title of any of those other books, but I had absolutely no trouble finding numerical methods that usually work. One small joke, and it made me remember that book for decades, right? So the last suggestion I have is mix in some humor, okay? Humor makes people remember things, okay? Now, of course, that brings up a kind of a difficult question, which is, are you funny, right? So let's say you're really funny, okay? Well, in that case, let me stand back and say, go with God. Just don't let the jokes get in the way of the explanation. But what if you're sort of funny? I think of myself as sort of funny. Sometimes I can make people laugh, right? Well, again, don't let the jokes get in the way. Subtle is better, right? That word is nowhere else in the title except on the cover and hidden there. Subtle is better. And don't explain the jokes. Jokes are not a place for explanations. All right, but now we come to the difficult case, right? There's always like the edge case, and it's what if you're not funny? What if you're not funny and you know it? Well, congratulations, you're way ahead of the people who aren't funny and don't know it. But it doesn't really matter. If you're not funny, it doesn't matter, because I said mix in some humor, but what I really mean is mix in some humanity. You need to show up at your explanations. If there is a prime directive in explaining, you can sum it up in 7 words. If you don't care, I don't care. Right? You need to care about the person you're explaining it to. You need to care about the thing you're explaining. Right? And that is the magic kind of elixir that makes explanations flow. So what do we got here? We have a plan, be agile, look for your explanations failing, go for specifics when you're talking about abstractions, watch the clock and put the terminology last, repeat yourself enough. Don't be afraid to repeat yourself in an explanation, and finally show up. But there's a funny thing about public speaking. I don't know if everybody knows this, but I think all people who do a fair bit of public speaking know it, which is that we don't like even numbered lists. 5 or 7, but never 6 or 4. So I do have a final really quick suggestion for you. And it goes like this. It is no secret that the world is kind of a mess. And contrary to what you read on the internet, that is not a new phenomenon. And sometimes it's overwhelming, right? We stand here and we think, I'm a single person. What could I possibly do to make things better? Well, I have a suggestion. Number 7 is my suggestion. My suggestion is this: make the person next to you smarter, right? I can't think of anything else that we can do almost without equipment, without resources. If you can help the person next to you understand something, you have made the world better. So with that, I hope you enjoy the rest of the conference. I hope you have a great weekend. And come Monday morning, I hope you roll out of bed and start explaining. Thank you very much.